Hello, students. Today we'll start a new chapter that is sound. Now, this term is very well known to you. Whenever any child comes to this earth, first, whatever we can hear, that is the sound. Okay, so that means we can hear the sound. So, now in this lecture, I will discuss the introduction to sound waves. I will discuss the sound characteristics of the sound waves and what is sound. So all these things we will discuss. Let's start. Now sound plays an important role in our life. Definitely, if I am walking and suddenly some car in front of me, then I can hear the horn, so I will be at the side of the road, right? So that means sound plays an important role in our life. If there was no sound at that time, there will be no conversation, whatever we are sharing now. So this sound, this is very, very important thing, and also without this, we cannot imagine our life. Okay. So this sound plays an important role in our life. Now, vibrating objects produce sound. I will elaborate this point later on. But before that, I'm just telling you, if I'm talking to you, now you can hear my lecture. That means what? You can hear my voice. So there is one part in our mouth that is called the larynx. And whenever it there is a vibration, actually whenever the sound you can hear, that means my voice box that will generate the sound by with the help of the vibration, right? So vibration vibrating objects that will produce the sound. Like you can see that speaker also. In that speaker, you can see very minutely. You can see there is a membrane here. There is a membrane here. Okay. So there is a membrane here, and this membrane is vibrating. This membrane is vibrating. So that means if there is some vibration at the loudspeaker's membrane or whatever the material they have, one type of screen, and that if they that will vibrate, then it will produce the sound. Now the vibrations, that is to and fro or back and forth movement of an object, and sound needs medium to travel. In vacuum we cannot see the sound, and in moon also we cannot hear the sound, right? Hence the it cannot travel in vacuum, that already I have discussed. So what we have studied here, sound plays an important role in our life. Obviously, without sound we cannot imagine the art, we cannot imagine our daily life. Without sound I cannot tell you anything, I cannot hear any sound, or there is no sound. It is unbelievable situation. So sound, it is an important thing in our life, important part of our life. And vibrating objects that produce the sound, as I have told you, we have larynx, this is the voice box, and due to the vibration inside our this voice box, there is a sound produced. So in case of speaker also, there is a screen, or there is a some one type of membrane made up of cloth type material. So there some vibration, there will be some vibration to and fro or back and forth movement, so it will produce the sound. Now, sound needs a medium to travel. One thing you can do, if you can see the loudspeaker, you just touch the opening. You just keep your hand in front of the opening mouth. In front of the opening mouth. That means I am saying this portion. In this portion, so you can feel some vibration. You can feel some vibration. And always for sound, we need some medium. Without any medium, that means in vacuum, we cannot The sound cannot travel. We cannot hear any sound if I am in the vacuum, right? So for this sound, we require the medium, like it may be air, it may be our water, but it should be some medium, right? Now, in these sound waves, in the picture, you can see one thing. There are so many air molecules are there, right? Around this speaker. This is called, just a minute. This is called speaker. Okay. Now, in front of this, there are several air molecules. These are air molecules. Now, you can see here some the places you have some concentrated air molecules here in this case, and here you have a very light amount of concentration. Where you have compressed amount of concentration, that is called compression, a very high amount of concentration of molecules and they are attached to each other, that is compression. And here that is rarefaction, that is rarefaction, right? So now you can remember what is compression and what is rarefaction, and I think that with the help of this picture it is very much clear to you what is compression and what is rarefaction. And this thing actually with our with only eye we cannot see this thing, but the air molecules that will vibrate, and due to the vibration of air molecules, some of the regions they will be rarefaction, some of the regions there will be some compression of the air molecules. Okay, got the point? Now the term whatever written wavelength I will discuss later. Now the introduction to sound, what we are doing, any sound like chirping of birds, like some guitar sound, any sound, whatever we are just going to hear, that here for guitar it is due to the vibration of strings. There are so many strings are there. So due to the vibration of strings we can hear the sound will be produced and it will travel through the air and it will just go to our eardrum. Okay, then we can hear the sound. The sound produced by vibrating objects and they travel from one place to another, that is called the sound waves. Okay, like wave it will flow, that is the sound wave. Now in this wave there is some pattern, and here there are two types of waves. One is the transverse wave, another is the longitudinal wave. Now the transverse wave, that means just see the pen. I am moving, I am moving like this, up and down, up and down, up and down, up and down. So this is called transverse. If I am moving left and right, 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 then it is called longitudinal. Is it clear? If I am moving up and down, up and down, up and down, up and down, top to bottom, top to bottom, top to bottom, then it is transverse. And if I am moving from left to right, left to right, left to right, then it is longitudinal. So in this picture you just see the transverse wave. The particles in here, we have several particles or molecules. Here the particles they move from up and down, up and down. So this is transverse wave. And here the movement is left to right, left, right, left, right. So this is longitudinal wave. Clear? Is it clear? So we have in this wave, there are two types of motion space here. One is the transverse motion and one is the longitudinal motion. So the transverse motion, that is called transverse wave, and here the longitudinal motion, that is called longitudinal wave. Clear? Now the transverse wave, as I have told, that particle motion is perpendicular in the direction of the wave motion. The direction of the wave motion along x-axis, and particle motion that is perpendicular from positive y-axis to negative y-axis. So that means particle motion is to perpendicular the direction of wave motion, right? And this type of wave is a mechanical wave called the transverse wave. Like light, example light. So this is the transverse wave. Okay. Now I will see longitudinal wave. What I have told, suppose this one is the axis x and I have the motion in this way. So if I am moving parallel to the x-axis, then it is the longitudinal wave. So when the particle of medium travel parallel to the direction of the wave motion by means of successive compression and rarefaction, how it will move? Sometimes compression, sometimes rarefaction, compression, rarefaction, compression, rarefaction. Here you can see that at this point, compressed. That means here you have compression. Here you have rarefaction. Is it clear? So here what we are doing, the process, these particles of the medium that travel parallel to the direction of the wave motion by means of successive compression and rarefaction. Okay, so this is the longitudinal wave. I think after these two slides, it is very clear to you what is longitudinal wave and what is transverse wave, right? Next, here this picture I have given just to clear this thing. This is the longitudinal wave. You have rarefaction, you have compression, you have compression. Here you can see that the transverse wave up and down are moving. So longitudinal waves are those waves in which particles of the medium, longitudinal waves are those waves in which particles of the medium move parallel to the propagation of the wave. Move parallel to the propagation of the wave. And transverse wave in which particles of the medium move perpendicular. Please remember this term. This is very, very important. Perpendicular to the direction of the propagation of wave. That is called transverse wave. Fine. I think after this picture there is no confusion in your mind regarding the transverse and longitudinal. Fine. If there is no confusion, we'll differentiate. Now, in case of differentiate, longitudinal, the medium moves in the same direction of the wave, right? And transverse, the medium is moving perpendicular, again perpendicular to the direction of the wave. Longitudinal, it acts in one dimension. Perpendicular, it acts in two dimensions. Longitudinal, the wave cannot be polarized or aligned. Here the wave can be polarized or aligned. This wave can be produced in any medium such as gas, liquid, solid, but this wave can be produced in solid and liquid. In gaseous transverse wave, there will be no transverse wave. The earthquake is an example. The earthquake S wave, that is an example. It is made of rarefaction compression and it is made of troughs and crest. I will discuss that crest rarefaction again. Now, what is sound? So, what is sound? Due to the vibration, the energy that propagates through a medium in the form of mechanical wave, that is sound. The medium in which it propagates can either be solid, liquid, gas. But vacuum cannot be. Remember this thing. Never say that in vacuum the sound can move. Sound travels fastest in solid, then liquid, then gases. That means its speed is highest in solid, then moderate in liquid, and slowest in gases. Okay. Now, a vibration, if with the help of physics we will define, then the sound, that is a vibration that propagates as an audible wave of pressure through a medium such as gas, liquid or solid. Okay. So sound, that is a vibration that propagates through a medium in the form of mechanical wave. Now, nature of sound. To define the nature of sound, we have to know the different characteristics of the sound like frequency, wavelength and amplitude. That I will discuss here. See here, this is the wave, and now what we know that, just a minute, what we know that this is the compression and this one is the rarefaction. Fine. Compression, rarefaction, compression, rarefaction, compression, compression, rarefaction, compression, rarefaction. In this way it is moving. So number of rarefaction and compression that occur per unit time is known as frequency of sound wave. Is known as frequency of sound wave. So frequency is the 1 divided by T. So the formula of the frequency is F equals to 1 divided by T, where F is the frequency and it is denoted by hertz. Always remember. And T, that is the time period. Okay. Clear? The frequency and time. So this is the frequency and time. Next, what is the wavelength of sound? See this picture very carefully. This portion, this is the compression, or this portion, this is the compression, and this portion, this is the rarefaction. So the wavelength, that means from one compression to another compression, how much is the length, that is the wavelength. So the distance between successive compression or rarefaction is known as the wavelength of the sound wave. The distance between the successive compression. This successive compression is very important because if I have the wave like this, so this is a compression, this is a compression, this is a compression. So the wavelength, if I will say wavelength is denoted by lambda, If I will say this is lambda, then I am wrong. I am wrong. So I have to take successive compression. That means I have to take this point and this point. I have to take the distance between these 2 points and this will be lambda. This is correct. And if you are thinking this, that is wrong. So the lambda, this is the wavelength and this is the distance between the successive compression and rarefaction is known as wavelength of a sound wave. So lambda equals to V by F. Okay. Next, the amplitude. The amplitude of the sound is the magnitude of the maximum disturbance in the sound wave. Now, if I have this waveform, maximum disturbance in the positive side is this much, maximum disturbance in the negative side is this much. So the amplitude, this is this portion. Amplitude of the sound is the magnitude of maximum disturbance in a sound wave. Okay. So higher the amplitude, higher the energy you have in the sound. Clear? Is it clear? So what we have studied? First we have studied frequency, then we have studied wavelength, then we have studied amplitude. So these 3 parameters, this will define your sound wave. Amplitude will define how much energy you have in the sound wave. Frequency will define how much completion rarefaction you have, and wavelength will define the distance between the completion, successive completion and rarefaction. Is it clear? Fine. Let's move to the next slide. Now, human ear can hear a limited range of frequencies. Now you know the term frequency. Now, human ear that can listen 20 hertz to 20 kilohertz. Kilohertz means 20 kilohertz means 1 kilohertz equals to 10 to the power 3 hertz. So 20 kilohertz, that is 20 into 10 to the power 3 hertz, that is 20,000 hertz. So human ear can or is able to listen the sounds which are in the range of 20 hertz to 20 kilohertz. But in laboratory condition, what do you mean by this laboratory condition? That means I have no noise. Surroundings, I mean, in my surrounding, there is no noise. Because whenever you are at in your home, you can hear the noise of the fan. You can hear the noise of any other objects also. You can hear the noise of sometimes the vehicles also. If your house is very nearby to the road. So that means in laboratory condition means if this room at that time the room is soundproof. That means no other noise can be there. So their laboratory conditions, human ear can listen 12 hertz, 12 hertz, low frequency as 12 hertz and high frequency 20,000 hertz. Clear? Okay. So how this is very important for your examination also. In MCQs also they can give this thing that the human ear, they can hear how much is the range, that is the 20 hertz to 20,000 hertz or 20 kilohertz. Now speed of the sound. Now I know that sound needs some medium to travel. Fine. But if I am giving the medium air, I am giving the medium liquid, I am giving the medium gas, already you will tell me, madam, already you have told that in air the sound speed is fastest and liquid it is moderate. And you have told that in gas medium that here you have some other speed. So that speed at which the sound wave propagates through a medium is known as speed of sound. And speed of sound is different in different media. So speed of sound is highest in solid, and because the atoms in solids are highly compressed, right? So here if I will tell air, that is the gaseous material, at that time it is fastest, that is a wrong thing, because it is fastest at solid. It is fastest as solid. Then in liquid it is moderate, gas or air it is low. Low speed is there, right? Let's see. Here why this low and high already I have discussed. Again I am discussing here. This is a solid where the molecules, they are very near to each other, and the molecules, the interatomic space, that is very less. But in case of liquid, suppose this is liquid, here you have this type of space, and in case of gas you have this type of interatomic space. Interatomic space means if this is one atom, this is another atom, then the distance between these two. So here you can see that in a particular area, huge amount of atoms are there or huge amount of molecules are there. So that means what? The interatomic distance is very low. So if it is very low at that time, you can see that in this case the sound wave, that this is the solid, this is the solid, and this is the case of liquid, and this is the case of gas. Here it will be fastest, here it will be moderate, here it will be low. Okay. So the interaction of the particle in solids is high. The speed of sound is faster than liquid and gases. So the speed of sound, that equals to d by t, where d is the distance traveled by sound and t is the time taken to cover that much distance. Time taken to cover that much distance, right? So that is the speed of the sound. Speed of the sound. Now several speeds I have written here. Water, that is liquid, 1481 meter per second. Air, that means gaseous material, 343.2 meter per second. See, low, very low. Copper, that is solid. Here you have the speed, that is 4600 meter per second. 4600 meter per second. That means very, 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 very high. If you just compare first three rows, then you can see that in the solid, it is very, 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 very high. More, 4 times than liquid. 4 times than liquid. And with respect to gas, it is very, very, very high. Okay. So this is the speed. So at least you please try to remember the water, air and copper this time. Now this is the experiment that I am telling you from very beginning. Yes, sound is produced by vibration. How, ma'am? I cannot feel the vibration in front of the speaker. So why, ma'am, you have told? Let's do the experiment. Sound produced by vibrating body. Here one tuning fork you just take, and this tuning fork is taken and one arm is struck on a rubber pad. There is a ball here, and with the thread I am just attaching this ball in this place. So suppose tennis ball you are just take, and that will be suspended using the thread. You can do it in your home also. Now this tuning fork you have. So here the arm of the vibrating fork, whenever it is very close to the ball, it jumps back and forth. It jumps back and forth, back and forth. And sound of the vibrating tuning fork is hard. Some, if you have gone to any ENT specialist to check for checkup, at that time also you can hear the sound. They are just hammering this on your forehead, and you can hear the sound with the help of your ear. So this experiment you can do with just one tuning fork you require, and this tuning fork, whenever it is vibrating and very close to this tennis ball, you can see that this tennis ball will move to and fro, to and fro. Why it will do this thing? Because there is a vibration, and when its arms stop vibrating, the ball becomes stationary and no sound you can hear. But when you can hear the sound, you can see that this ball will move to and fro, to and fro. So this experiment you can do it. This is very, very interesting experiment. Now next experiment I will do. What? The material medium is necessary. You have told me, ma'am, in vacuum it is not possible. In air, gas, liquid, every medium it is possible that sound will travel. But in vacuum it is not possible. Why I will agree this thing? I will do one experiment. Ma'am, you just tell me the experiment, I will do it. Fine, you do it. Here, you just take one electric bell that is suspended inside an airtight glass bell jar. This is the airtight glass bell jar, and this bell jar is connected to vacuum pump. is connected to vacuum pump as shown in figure. As the circuit of the electric bell is completed by pressing the key, here you have the key, this is the switch or key. The hammer of the electric bell begins to strike the gong repeatedly, due to which sound is heard. You can hear that gong. There is a sound. Now you do another thing. Keeping the key pressed. Keeping the key pressed. Air is gradually withdrawn with the help of this vacuum pump. Now you will notice what? You will notice that the loudness of sound goes on decreasing. As much as you are just taking out the air, the loudness of the sound that will be decreasing. Finally, whenever fully airtight bell jar is empty, there is no air inside the bell jar, you can see that there is no gong, no sound. So the hammer of the electric bell is still seen striking the gong repeatedly, which means that sound is still produced but it cannot be heard. That means sound is not traveling. Just you do this thing. Why you rely on me? You just take one vacuum pump. You just take away all the air from the bell jar. You examine this thing. So you will see that you cannot hear the gong sound whenever there will be no air inside this bell, right? So in this way, whatever I am telling you, you can do it in your home. You can do it. Just you have to collect a little bit things, and I don't think that it is very much costly. So you can do it. So that proves, these experiments prove that for to travel the sound, we require what? We require air or any medium we require. Now the propagation of sound. Now sound waves that move from one point to the listener through a medium, that we have understood using experiment also. Some vibration will be there, that also we understood using the experiment also. Yes or no? Yes. So the particle passes on the vibration to its adjacent and neighboring particle. That is important. Now the first particle comes back to its equilibrium position of rest. Then the second particle passes its vibration to the neighboring third particle. Then again comes back to its position of rest. Like whenever all of you are sitting in a bench, suppose all of you are sitting in a bench, one particle, second particle, third particle, fourth particle, fifth particle, it will vibrate. When it will vibrate, it will just pass this, vibrate, then passes this vibration to the next person. If it will vibrate, then it will, this will vibrate, then it will vibrate, next person will vibrate, next person will vibrate. That means what? The vibration is coming from this point to this point. The vibration that is coming from the first person to the last person. In this way, you have in the air or any medium some particles, and each and every particle that passes the vibration to the adjacent or neighboring particle. Whenever everything is complete, at that time there will be equilibrium position or rest position. Now propagation of sound. This process continues the vibration until the vibration reaches the listener and he is able to hear the sound. Now here you can see that this is the wave motion. Now this is the wavelength. This is the wavelength, already I have discussed. Now I have told you, whenever there is some transverse wave, at that time you have some crest and throw. Okay, crest and throw. Now you see here some density vibrations in case of the medium particle, and this is the pressure vibration. So if density and pressure we take, then we will get average density and pressure at that time with the distance. Distance between what? Distance between the source of sound and listener. In between these two, distance between these two, at that time you can see that it is the only the vibration that travels through the medium, and this is called wave motion. This is called wave motion. Okay. Now, the propagation of sound, this is a mechanical wave you can see. Why I am telling this mechanical wave? Because all the vibrations you have here, and due to the vibration in this area, you have the vibration in the next area, next particle. So that's why I'm telling this is mechanical wave. So wave is a disturbance that moves through a medium when the particle of the medium set neighbor particles into motion. So this is mechanical wave. Mechanical wave. And you should remember crest, throw, wavelength, obviously up to this much. These things you have to remember. So the sound propagates due to what? Due to compression and rarefactions. Compression, rarefaction. Compression, rarefaction. Here, C, that is the and R. Here, some points are here. You can see that this is C, that is compression, and R, that is denoted by rarefaction. Okay, so C R like that it has been written. Compression, rarefaction, compression, rarefaction, compression, rarefaction. Okay, so compression means when the vibratory body moves forward, it pushes the or compresses the air ahead of it, thereby creating a region of high pressure and high density. What happens? If suppose in a room you have so many students in a room, if someone pushing you, what you will do? You will push another particle, yes or no? That means, or you can do one thing, that you are compressed, you are just after push, you will be compressed. So when these particles also they are doing the same thing. This particle, what it will do when a vibrating body moves forward, then it pushes or compresses the air ahead of it and creating a region of high pressure and low pressure. Here you have the low pressure, here you have the high pressure. Okay, so high pressure and then low pressure. So that means these are called the compressions, where you have the high pressure and high density. These are called compression. Same as where you have the low pressure and low density, that is called rarefaction. That area is called rarefaction. So this is the rarefaction that just now I have told you. Where you have low pressure and low density, that is the rarefaction. Okay. So the peak of the wave is called crest and the valley of the wave is called throw. So this is the valley and this is the peak. Okay. And sound wave are longitudinal waves. The individual particle of the medium move in a direction parallel to the direction of propagation of the disturbance. I have told you, if it is longitudinal, obviously it should be parallel. It should be parallel. If it is transverse, then it should be perpendicular. So the particles do not move from one place to another, but they simply oscillate back and forth, back and forth. left, right, left, right, left, right, like that, back and forth, about their position of rest, thereby propagating only the disturbances from one place to another. Clear? Okay. Now that means due to compression and rarefaction, we have the propagation of sound wave. Fine. Till now, it's okay. So thank you. Next lecture, we will discuss more things regarding